Hello everyone, welcome to what will be our pre-lecture number 36. We're going to talk about nuclear chemistry today. So just a couple reminders here about what a nucleus is and what's contained within it. We have protons and neutrons within the nucleus. I think this was the first thing we talked about in Gen Chem 1. But to round out Gen Chem 2 here, we're going to be discussing nuclear chemistry, which involves changes in the nucleus. And so the rest of chemistry is basically changes in electrons or bonds. It's what we've been talking about for about 8 months, and so we're going to finish where we started. Just some reminders, when we have our atomic symbol, we can have different isotopes, and so that is going to be indicated by our mass number, as to which isotope it is, and then this Z term is our atomic number, which in some ways is redundant because the atomic number also determines the chemical identity of our system. So for example, if we have 6 protons, we know we're always going to have a carbon atom. And so sometimes we don't see Z included in our chemical symbols, but just have the element instead. Okay? So with that in mind, let's talk about radioactivity, which is the spontaneous emission of particles and or radiation from a nucleus due to instability. And so we have 3 main types. We're actually going to talk about some others as well, but the 3 main types are alpha, beta, and gamma, shown here. And so alpha, and so I should say, not shown on this slide, but we can eject protons or neutrons. Those are rare, so we're not going to really discuss them in depth in this class. But the 3 main types again, alpha, beta, and gamma. With alpha particles, what we're doing is ejecting a particle that has a mass of 4 and 2 protons. And so if you couldn't guess it based on that, if we have mass number 4, 2 protons, an alpha particle is the same thing as a helium atom. Okay, so this is basically ejecting a helium. We can also eject beta particles, and that can be a negative beta particle or a positive beta particle. So a negative beta particle, equivalent of an electron, and it's not that we are ejecting an electron that is already present in our atom. This is an electron that comes from the decay of a proton or a neutron, and we'll talk about that. And then a positron is the reverse of that. So it is an electron-like particle, but instead of being negatively charged, it has a positive charge. And we'll talk a little bit more in depth about both of those. Then finally, our strongest radiation is gamma rays, and those are extremely high energy and kind of the radiation that everyone is most scared about most of the time. So just one additional route that we'll talk about, we can undergo something called electron capture, and that will lead to other radiative events. And so let's dig a little bit further in to radiation. And so 2 things that we often care about with radiation are the ionizing power, which is the ability of that particular radiation to ionize another molecule. And we also have penetration power, which is the ability of the radiation to get through matter. So not just be absorbed by matter, but go through it. And typically when we have a large mass to our radiation, so something like a helium atom relative to a gamma particle has a very large mass, and we would say that has a high ionizing power and will cause more damage. And I'm realizing that I flipped this. A large radiation means a small mass. Sorry, I should have included that. And a small radiation means a large mass. And so it has greater penetrating power, but causes less damage. And so this figure is basically the key here. Alpha particles are, as long as you don't ingest them, they are pretty much harmless. But if you do ingest them, they can actually be incredibly harmful. There have actually been some reported assassinations carried out where people put an alpha-emitting isotope into someone's food, they ingest it, and it emits alpha particles and actually slowly kills someone. Beta particles are in the middle, so they can accumulate in specific areas of the body and cause damage. For example, we actually have radioactive iodine that localizes in the thyroid, and that can be used to actually treat thyroid cancer. If you have radioactive calcium, that can isolate in your bones. And gamma radiation is very ionizing, so it can damage immature cells. But if we think of our penetrating power, just to give you kind of a baseline here, an alpha particle can be stopped by a sheet of paper, or your skin, so not very difficult to stop, whereas a beta particle can get through a sheet of metal, particularly if you think of like aluminum foil, that it would be capable of stopping a beta particle, or a piece of wood. Once we get to gamma radiation, you basically need slabs of concrete or several inches of lead in order to stop it. So gamma radiation rather is extremely high penetrating power. Okay. And so within that, we have ways of measuring radiation. The Curie is a measure of exposure to radiation in honor of Marie Curie, who is kind of the godmother of discovering nuclear radiation. She named the elements radium for its radiation, and polonium, which is named after Poland, which is where she was from. And then later on, she actually had an element named after her after she died, curium. So she's all over the periodic table, pretty much straight boss, and also has the unit of radiation exposure named after her. We also have a gray, which measures the amount of energy absorbed by body tissue. So 1 gray is 1 joule per kilogram of body tissue. We also have rads, which are essentially a centigray. They are still amount of radiation absorbed by body tissue. And then what we typically report radiation in are units of REMS, which are your rads times another basically fudge factor or biological effectiveness of the radiation. So that will be dependent on the type of radiation that your body sees. So something we call RBEs, and when we multiply those two, we get REMS. And REMS stands for Roentgen Equivalent Man, which Wilhelm Roentgen was another scientist who actually discovered X-rays. So this picture here is actually the very first X-ray ever collected, and it was the patient was Wilhelm Roentgen's wife, and so he took this image, showed it to his wife, and she nearly divorced him because she thought that he had cursed her to death, and basically got images of like skeletons in the Grim Reaper because of this image. And so it was quite a marriage kerfuffle, the discovery of X-rays. Anyhow, let's talk more specifically about different types of radiation. So again, we have alpha particle radiation, which is producing a helium atom, which is the equivalent of a helium particle. And notice here that we have a balanced chemical equation when we write this. So if we start with a uranium isotope that is a mass of 238, we would call this uranium-238. If it undergoes alpha decay, it produces thorium-234 because we take away 2 of our protons, which changes the identity of our element, and also our mass number. And then we produce an alpha particle as a result. We also have negative beta particle decay, which is us turning a neutron into a proton. So you'll notice it turns from gray to red here. That is a neutron becoming a proton. To do that, it ejects an electron as a negatively charged beta particle. Okay, so that will also then change the identity of our element. So an example of that could be radium converting to actinium, where we don't have a change in our mass number, but we do have a change in our element identity because we change a proton, or a neutron to a proton rather. Basically, same way, same thing, but going in the opposite way. If we get a positron emitted, we convert a proton to a neutron. And so an example of that would be phosphorus 30 going to silicon 30, where again, we decrease our atomic number this time by 1 and emit a positively charged beta particle, which we tend to call positron emission, which this might sound familiar if you've ever had a PET scan. That is a positron emission tomography. This is a way that we do some medical imaging, is actually the radioactive decay of phosphorus-30. So very interesting, I think, at least. Okay. Then we also have electron capture. So when we get very large, very massive nuclei, then they can occasionally capture an electron from their inner shell, and that results in the conversion of a proton to a neutron as well. This is essentially the reverse of a beta emission, and we emit some sort of radiation, usually an X-ray, when that happens. So an example of that could be ruthenium-92, capturing an electron, so adding a negatively charged beta particle, turning into technetium-32, which is the element right next door to ruthenium. Then finally, we have gamma ray emission. So an example of this might be uranium-238 undergoing an alpha decay, so kicking off an alpha particle, turning into thorium-90. But we can also produce extra radiation with that. So this is emitting a gamma ray. Typically, this happens after we have a different kind of radiative event and our nucleus remains in what we would call an excited or a metastable state. And so that excited state has to decay. It decays by emitting that very high energy radiation in the form of a gamma ray. Another example here that is also used in medical imaging is technetium-98M. This M is for metastable, decaying where we don't actually change any mass units or number of electrons or anything, but we're able to go from this excited state or this metastable state to a more stable ground state and emit a gamma ray. Okay? So some practice that I would like you to do before class that we'll go over in class: write a nuclear reaction for positron emission of potassium-40, and write a nuclear reaction for the electron capture of iodine-111. With that, that is the end of this pre-lecture. If you have any questions, please let me know. Otherwise, I will see you soon.